Hey everyone, and welcome back. This is Fluence's Tech Talk series, and this is Tech Talk number 3. I'm Jason Bowman, and thanks for joining. Today we're going to be talking about meat processing operations specifically. What I want to discuss is the typical operations and what we can do as water and wastewater professionals to build a better wastewater management practice as well as create more sustainability. So we'll talk today about waste to energy and how this can be applied more holistically to these facilities so that we can create net positive energy operations. Thanks. Okay, so before we get started, full disclosure, some of the subject matter here today may be a bit sensitive, but whatever side you land on, let's agree that this is in the interest of promoting better wastewater management practices as well as more awareness. So firstly, the meat processing industry is very smart. Do not kid yourself. They know what they are doing. The number of sheer mechanical and biological and bioscience innovations created from this industry over the past century is mind-blowing. Additionally, this industry has a massive economic impact. So the US alone generates well over 1 trillion, that's with a T, of economic activity and economic impact. So this is an extremely sophisticated industry, and for what it's worth, they're very savvy when it comes to creating value. So keep in mind that a number of commercial products are generated because of upscaling created within this industry specifically. So this industry fuels secondary businesses like animal feed, fertilizer, alternative fuels, health supplements, cosmetics, etc., on and on. However, as we all know, the meat industry is under a microscope when it comes to regulatory and public concerns over pollution and energy. So how can we as water and wastewater professionals help create a more sustainable operation and add value? Well, the short answer today is going to be waste to energy. We have a particular strength in managing meat processing wastes, and we have developed systems capable of providing net positive energy operations within economical reach. So welcome to Tech Talk number 3, and I hope you enjoy the next few slides. Okay, so let's start by understanding the basics of meat processing, the 30,000-foot overview. No matter what type of meat we're processing, materials from the processing are typically identified in one of 3 areas. So number 1, we have desired product. Number 2, we have product-specific wastes. And number 3, we have non-product specific waste. So that can be anything from washdown to CIP processing. At the end of the day, non-product specific waste and residuals from product specific wastes can no longer be upscaled and therefore provide no further commercial or operative value. This is essentially what ends up at the head of the wastewater operation. So these residuals contain fats, lipids, organic solids, et cetera. Collectively, this makes it essential to have the right type of primary treatment step in place because you really cannot put this down the drain to a sewer system, and obviously you can't send it direct to surface water discharge. So how do we continue to create value and sustainability when dealing with what is really considered an unwanted waste? Well, we as Fluence make this a wanted waste. Most meat processing operations view this waste management as a cost, and historically that has unfortunately been true. But much as the physical processing side has evolved, so have waste management practices over the years. So from here, what I'd like to talk about is a typical waste management operation, the options available, and ultimately how we make this waste unwanted waste that can generate energy for us. Okay, bear with me because this is going to be a long one. If you've ever seen wastewater operations at these facilities, then more than likely you've seen dissolved air flotation, or DAF for short. So allow me to harp on this for a minute because it's a crucial step in making waste wanted versus just a cost. Just note that this is not only our perspective, but there is some science behind this. So DAFs are typically one of the critical first steps in these facilities. In some cases, this is the last effort for these operations to collect the final bit of residual fat or grease, which is and can be key for maximizing the rendering operations. But like many sites, this is simply the most cost-effective primary treatment step prior to sending waste down the drain. So let's talk about why DAFs are generally used for a second. So bear with me. A typical thought process usually goes something like this. All right, me as Mr. Operator, can I send this directly to the sewer? Well, given the type of waste, it's impossible to dump untreated effluent down the sewer or send it to a surface water discharge. Not only is it a health hazard, but it creates physical issues and blockages and odors in sewer systems. Okay, so then me as Mr. Operator, I need some basic form of treatment. What's the easiest, what's the most cost effective, and what requires the least amount of real estate? Well, the answer is you might get one of those, but not all three in one system. So given the nature of the waste, there are a few options. First, okay, what process is easiest and can handle this waste with minimum mechanical treatment? Well, historically, the answer has been lagoons, and more specifically, covered anaerobic lagoons, due to their ability to capture biomethane, but also provide an odor buffer. But these lagoons require a tremendous amount of land. A typical design starts with roughly 1,000 pounds of BOD per acre as a loading rate. And these systems can have hydraulic retention times required on the order of 30, 40, or even 50 days. So let's say a 1,200 to 1,500 head cattle operation produces roughly 1 million gallons of wastewater on a daily basis. We would require a minimum of 30 million gallons of lagoon volume if we're going to go with a lagoon process. So if you figure your lagoon is 10 feet deep, you would need roughly 10 acres of land to receive, digest, and treat this amount of waste. Okay, so wait, I don't have that much land. Now what? Well, your main option at that point is then to think mechanically. Now, remember, lagoons are simple. They require very little, if any, mechanical treatment up front. But if you don't have the land, the best way to reduce your land is to think mechanically. So by thinking mechanically, we're now going to remove specific contaminants that would then allow me as the operator or the facility to reach a level where I can discharge to the sewer, maybe have some surcharges, or I could even use a mechanical system in operation with a biological system, and now I could treat down to a point where I could even go to surface water discharge. So let's talk about those options in more detail. Okay, so in continuation, I either need pre-treatment like a DAF and still possibly have to pay surcharges, or I need pre-treatment with a higher rate biological system to minimize or eliminate my surcharges, or I need a massive lagoon. Well, by the way, if you are in a rural area, which many of these facilities are, there is no sewer connection. So then you're really stuck with surface water discharge or irrigation. And again, oh, by the way, this typically requires that you remove up to 99% of your total pollutant load to make this possible. Generally speaking, a DAF has the highest aerial efficiency. It's 5 to 10 times higher than most solids separation process, such as a gravity clarifier. It also provides a much better separation mechanism for fats, oils, and greases. So this is why you see DAF systems applied to these specific wastes at most facilities. At the end of the day, a DAF unit is arguably the best pretreatment option. Whether you like a DAF system or not, unfortunately, it's true. It is a chemical cost, it is an operating cost, but there's not many systems out there that do a better job per unit area at separating this type of waste. So now I want to provide a slightly different perspective. While DAFs do an excellent job at removing solids, fats, oils, and greases, they do nothing for soluble and dissolved matter, meaning that things like soluble COD and ammonia are still largely present in the effluent. So let's focus on that for a minute before we get into waste to energy. Well, how do we treat from here? Well, we've already discussed option one is really DAF and pH adjustment, basically send it straight to the sewer. This option is the easiest typically, but it still carries a surcharge in most situations. And there's really no other value created here simply than having the easiest mechanism for many treatment facilities. The second option is to add biological polishing, whether it be an aerobic polishing or a combination of anoxic and aerobic polishing. So many facilities opt for this option to lower the COD, ammonia, TSS, and total nitrogen in some situations. So in a lot of cases, this will drastically reduce the surcharges, and in some cases, it can eliminate surcharges if it's designed correctly. But still, if we look at the 1 million gallon per day facility that I previously mentioned, I would expect anywhere from 4 to 5 tankers of biological sludge to be generated So again, we're balancing that surcharge cost versus the equipment cost now versus a hauling cost associated with biological sludge. So again, at the end of the day, there's really no value created here other than finding a way to balance your operating cost and your capital cost. So the final option, and this has historically been true, but is now changing, has been anaerobic biological treatment. So as I mentioned in a previous slide, anaerobic treatment or anaerobic lagoons specifically were used historically because they are, quite frankly, one of the simplest mechanisms for taking this waste directly with having no or minimal mechanical pretreatment ahead. So for older facilities, this used to be very common, but obviously it requires a significant amount of land. Here in my home state of North Carolina, this has been a very common practice, but now land is becoming a hot button. So what if we look at higher rate anaerobic system? Well, again, to use a higher rate anaerobic system, you do have to go back to a mechanical pretreatment step. High rate systems can't take this type of waste directly. So typically we would still need to use a DAF that's removing a lot of the FOG and a lot of the solids before this can be applied. But still, again, using that 1 MGD facility, a 1 MGD worth of flow into a high rate anaerobic system still requires a rather large and expensive high rate anaerobic system. But keep in mind that DAF, while it's taking out the solids and FOG, that DAF is also taking out most of the potential energy from the operation. That is the lipids, the caloric value, and the waste to energy value. So talking about a high rate system after a DAF in a lot of situations doesn't make a lot of sense because there's really much less potential energy in the remaining wastewater. At the end of the day, as I said in most of my tech talks, the site location, the site logistics, the local regulations, and local costs often drive which of these options are manageable for these facilities. But of these options, where are we creating value? Yes, the anaerobic lagoons do add some value simply because they do have a biomethane potential. Well, I want to circle back to the DAF. So remember the DAF that we spent so long discussing. It turns out that the solids and the sludges removed in the DAF process contain an exceptionally high caloric content, and therefore the potential energy that could be created with this waste is higher than the remainder of the entire wastewater operation in some situations, actually in most situations. So most operations view this sludge as a disposal cost, or an unfortunate side effect of operating a physical chemical pretreatment process. So while we've focused on how we're going to discharge after a DAF, we've recognized that DAF is ideal in most cases, but still the solids that the DAF is removing is something that we really haven't honed in on yet. So there is a solution that would enable us to create a significant amount of value from something that otherwise these facilities view as an ongoing headache, and that is the DAF sludge. So not to get too far ahead, but this is a particular strength of Fluence, creating value from DAF sludges. And this waste to energy is how we can create a net positive energy operation. All right, so picture this. All of that DAF sludge that you're currently hauling off-site goes into a landfill, or perhaps it goes to a regional digester. Either way, it's likely costing you a lot of money. What if we could design a digester on-site to reduce that sludge volume, let's say 80 or 90%, and it could potentially generate more energy than the remainder of the entire waste management operation requires? So let's try to break this down and put it into perspective. DAF sludges will typically constitute anywhere from 3 to 5% of the incoming flow. In other words, for that same 1 million gallon per day facility, I would expect that roughly 30 to 50,000 gallons of that are converted to DAF sludge on a daily basis. So we know that DAFs typically remove up to 90% of the TSS, that is organic solids, 90% of the fats, oils, and grease, and potentially some COD in some cases. So 1 ton of that DAF sludge can generate over 1,500 cubic feet of biomethane on a daily basis. So with 50,000 gallons produced, we're talking about 200 tons per day. So that's 200 tons times 1,500 cubic feet of biomethane. Another way to look at this is The DAF is really removing most of the calories and the energy from the wastewater. So these sludges are highly volatile, full of lipids, and full of organic matter. This is a perfect condition for anaerobic digestion. Conversely, the clarified wastewater that leaves a DAF, that is the DAF effluent, is, relatively speaking, void of significant caloric content. So for us, it really makes no sense to target anaerobic digestion after a DAF operation. It's really an expensive endeavor, and there's very little energy yield compared to the energy that you could yield from a DAF sludge. So how about the size of these systems? Well, again, taking that same 1 million gallon per day facility, so that's roughly 1,200 to 1,500 head of cattle by comparison, or 200, 300,000 chickens by comparison, we would typically require anywhere from 1 to 1.5 million gallons of digester volume. So compare that to the historical and conventional anaerobic lagoon that required 30 million gallons. So we're talking about roughly 1/30th of the size of traditional systems. So by digesting this waste specifically, it is usually possible for a 1 million gallon per day facility to generate upwards of 30,000 to 40,000 kilowatt hour of clean energy on a daily basis. So if we expand that and look at in terms of annual operations, this is essentially the same as saying that we're taking over 11,000 tons of CO2 out of the equation, or taking 2,400 gas-powered cars out of the equation, again, on an annual basis. Or, to put another way, this is the same amount of annual electricity that 2,000 homes would require. So, for those of you who are interested, please check out the EPA website on equivalent energy and kilowatt hour avoided calculations. So here in this table, what we're trying to show is the relative energy value based on the various waste sources that we find at these facilities. So now we can paint a picture as to how we are creating value from what is otherwise a nuisance or a massive operating cost for these facilities. At this point, I'm sure most of you are asking, all right, well, how much am I going to save, or how much is this going to cost me? So to put this into economical terms, most of the facilities that we work with that are 1 MGD or higher look to save over $1 million per year in operating costs. So roughly $1 per gallon as a operating savings. Generally speaking, we find the ROI for these facilities is normally on the order of 2 to 3 years, but on occasion it can be lower pending the exact site conditions and the exact makeup of that DAF sludge. Now, keep in mind this ROI is on its own merit, so this does not include any of the current tax credits that might be available under the IRA. So not only is this approach economical, but it provides a much more holistic and much more sustainable operation for most of these facilities. So there's nothing like seeing an actual case. Fluence specializes in this type of industry, and we've developed methods for taking DAF sludges, but also other byproducts you may find from other facility operations. So in this example, we show a 1,200 head operation noting the energy generated by feed type. So that is energy by DAF sludge, by solid waste, by tallow, and rumen. While we spent a lot of time discussing DAF sludges throughout the presentation, it's also possible to add other byproducts to boost biogas potential and or simply to reduce the burden of hauling all this unwanted waste away. So based on this example, you can see the facility utilizes a 1.5 megawatt CHP process to generate enough energy to completely offset the energy used for the remainder of the waste management operation. So here in the foreground, you can see our T-ARC solids digester. This is a 1.3 million gallon system for perspective. So on a similar note, we can look at poultry operations as well. So poultry operations also provide an opportunity to generate significant clean energy from their operations. Note the digester volume here in relation to the facility flow. So here we're using a 790,000 gallon T-ARC high solids digester, where in the previous example for the 1,200 head of cattle, we had just over 1 million gallons worth of digester volume. So here, this poultry facility is producing well over 50,000 kilowatt hours daily combined energy by taking a combination of DAS sludges, biological system sludges, and rendering effluents. And there we have it. We've learned that we can create significant value and add value for these operations from something that is otherwise being disposed of or viewed as a nuisance. So if we were to tally up all the energy produced across all the operations that we're involved with, we would be in the hundreds of gigawatt hours. So it's a significant amount of energy out there to be made. If we also look at the CO2 emissions, by not using traditional energy sources and using biogas or biomethane as an energy source, we're actually saving more CO2 emissions than some small countries produce. So that's actually mind-blowing. For anyone inquiring about how to treat the digestate, that is what comes after the digester or comes out of the digester, please circle back to Tech Talk number 2, where I focused on managing digestate. So please join me next time for Tech Talk number 4, where we will again focus on meat processing operations, but how to remove nitrogen and phosphorus from these wastewaters. Thank you. Keep it clean.